Good afternoon, good morning, everyone. Welcome back to our 5 webinar sessions, coffee break session hosted by ISCOB together with AST Environmental. Today, we're gonna touch base on one of the technologies that we use for in situ remediation. So we will cover the ISCOB and RPI group relationship that has developed over the years in implementing the trap and treat technologies. We will go through for this session, the BOS 100 and CAT 100 technologies that have been used now for almost over 20 years worldwide, pretty much. We have a number of case studies that we would like to present briefly to get you acquainted with the data development that you could expect out of a remediation performed with BOS 100 or CAT 100. And as all the other sessions, we will leave as much time as possible for a Q&A session. We would like to remind you the upcoming sessions that we will cover during the next few weeks. So on September 14, we have planned to follow up on the trap and treat technologies session by covering the BOS 200 and BOS 200 plus technologies, which are normally used for, let's say, hydrocarbon type of contamination. And then on October 3rd, we'll wrap up with the latest addition to our suite of technologies used for in situ remediation, which is the fluorosorb by Setco, which is used for PFAS remediation, which is slightly different from the technologies that we use for normal organic contamination. And we will learn more about that. So as a quick introduction, again, we may have covered this in the previous sessions, but just to wrap up a bit where we come from as ISCOB within the RPI group. So ISCOB was founded back in 1999, and due to its geographical position, we are out of Aarhus, Denmark. We have been active mostly across the Nordic region in Europe, but we have been covering over the years most of Europe, and we have entered China with high-resolution site characterization and in situ remediation also from 2015, 2016. Back in 2010, ISCOB has become a licensed installer for the RPI Remediation Product Incorporated group, for the installation and use of the trap and treat technologies. And recently, last year, we have been also introduced to this new technology by Setco, which is fluorosorb for PFAS remediation, and we have become similarly a licensed installer for injection application. What we do at ISCOB that we try to make sure we replicate for all our clients is to provide as much as possible total solutions, given the variety of the tools that we have available in-house, covering from MIP investigation to high resolution, high density, high frequency soil quantification. We have this great support from RPI that has, since its foundation, provided clients with free of charge analysis of soil and groundwater samples. And we have probably estimated up to 150,000, if not more, samples analyzed over the years from cradle to grave. So we try to support our projects from the design through the implementation, all the way to the performance and closure by helping clients reducing their operation and maintenance cost when it comes to monitoring. Within our group of installers and AST as a main sort of national and global distributor of the technologies through RPI, we have hundreds of years of combined experience when it comes to both the design and injections of slurries and solid amendments. It's not as easy as when you have like compounds or products that can be dissolved in water. Over the years, we have implemented thousands of projects, and we have been installing over 10 million kilograms of BOS products combined with additional supplemental amendments. And as ISCOB, we have been probably part of that installation process for 7-8% of that. Our success rate is not measured by how many projects we perform or we have been performing over the last 20 plus years. We rather look at how many clients have come back to us and do more and more work with us. And that number sets at 95%, which means that many clients understand the approach, understand the design and implementation parts that goes along with our technologies and come back and want to do more. And we have covered pretty much all the globe by injecting in all the 5 continents, more than 15 countries globally, and across the US, we have covered more than 90% of the whole territory. Mike Mazzarese, that is here today with us, I would like to leave you the word to talk a bit more about the technologies.
Thanks, Giorgio. So we'll just spend a few minutes here covering the 2 technologies that we're going to cover today. If you're interested in more information, we have standalone webinars that sort of do a deeper dive into each of these. So due to the short format of today's webinar, we're just going to cover these briefly on just one slide each. So BOS 100 is the original chlorinated solvent technology that was developed by RPI, and it's very simple but a very elegant technology. It's activated carbon that everyone on this call, I'm sure, is familiar with, and they take activated carbon and they impregnate it with reactive iron. So those of you that are, I'm sure most of you are going to be familiar with zero valent iron chemistry, and it's that same abiotic pathway where you go through the beta elimination pathway to generate, say, starting with PC, TCE, you're going through the acetylene, ultimately the ethylene route. The advantage of it is that you don't generate daughter products as part of that process. And so as you'll see in some of the case studies we're going to present, it's an excellent, we consider it best-in-class technology for PRBs. And we'll show you that here in a little bit. And there's 6.5% iron by weight that is impregnated within the activated carbon. But what we and RPI over the years determined is that source areas, especially DNAPL or suspected DNAPL sites, there isn't enough iron to treat, because we want to design around the iron content, around the treatment mechanism, which is really important, not just the activated carbon. And so RPI developed maybe 7 or 8 years ago now, CAT 100, which is a modified version. So it uses BOS 100 as its base, and we add an electron donor, we add some nutrients, and then we add 2 bacterial consortiums, one to break down the electron donor into smaller molecular pieces, and a second suite of bacteria that are dechlorinators. And so what you'll see is anytime you add an electron donor to the subsurface, you are going to generate some daughters. But that combined with the BOS 100 PRB, as you'll see, is a really nice combination of technologies to be able to make sure that you don't have daughter products or any parent or daughter products leaving the subject site.
Thank you, Mike. And yeah, we have covered this part about installation in the previous webinar, but it's just to sort of, again, highlight the fact that it's not just about the technology, but it's how you implement it in the field and how you install it. So we have been covering previously the importance of the remedial design, so understanding where the mass of contamination resides and how it migrates off-site, and make sure that you have a correct understanding of how you want to play with the contamination based on the site conditions. And ultimately, injecting these products requires a lot of energy, both when it comes to the mixing process and especially then for the installation, as we are dealing with granulated activated carbon. So we just want to highlight again the fact that when we inject, we normally work around the triangular grid spacing that can vary between 1.5 meter to 2.3, 2.5 meter. And we make sure we do only top-down injections to ensure that we inject exactly in the intervals that we are targeting. We advance every 0.5 to 60 centimeters at a time. We have custom built system that can be set to work within pressure ranges that go from 0 to 170 bar. We can adjust the flow rates from 30 to 920 liters per minute, and ultimately also play with the exit velocity, which is what you truly need to be in control when you deal with different type of geologies. So as you are in clay soils or sandy soils, you will have to make sure that you use the right exit velocity. For this reason, the key parameters that we look at are generally the pressure that we work at, the flow and the exit velocity, and the injection volumes and the density, and how to control all of that. As everybody's probably aware, daylighting is one of the things that can happen in the field when we work with injections. And that's exactly why you need to be in control of the design, ultimately of the goals that you are trying to achieve for the remediation, so that you can play with your spacing grid while you're in the field, adjust the volumes, adjust the densities, but ultimately know how your product works and how you need to install it to ensure that the client still gets the best result. And as Mike was mentioning, we have a number of case studies that we would like to this is an example of, how the high pressure injections are performed. We move on to the case studies. So we want to show 3 case studies that we have at hand for today. The first one is a site in Northern Europe that we entered working in 2016. At that time, the client had already been performing a number of remediation attempts. They had been removing the USTs that were used for PCE storage between the 2 buildings that you can see on this map. No matter what, there was a major plume that was leaving the site, causing the local municipality to have to forbid the local property owners to pump water from their garden wells. That has led the client to try to find a solution to stop using pump and treat systems, soil vapor extraction systems that ultimately were not able to provide a closure to the site. When we were approached in 2016, the first question that we were asked was, could you give us an idea what could be a cost or a solution to stop this plume from migrating off-site? And the initial intention from our side, without the remedial design that we ended up doing, was we could install a big PRB at the site boundary and try to contain that plume from migrating. The client invested money into a remedial design characterization. We went back at the site. We actually found out that there was a massive source at the actual inlet of where the tanks were filled in back in the day. So we found a DNAPL pool that summed up, when we did the whole quantification by high density soil sampling, to about 16,000 kilos of PCE present in soil. And that budget that we initially discussed with the client being feasible for the installation of this PRB was actually shifted to a source treatment. And that allowed us to tackle the source area a lot more effectively by use of Cat 100. And as we look at the data, this is what happened. So as we started the remediation, we had this massive plume, as you can see, with concentration still up to 100,000 microgram liter of PCE at the site boundary. Ultimately, the target long-term with the authorities is to reduce those concentrations to about 10 microgram per liter of PCE at the site boundary located where I'm moving the cursor of the mouse right now. The latest data that came in over the years, so the client here has invested a lot of time in monitoring the site. Through the support of RPI, they managed to save about 70,000 euros just worth of analysis that we provided free of charge. And the results are clear. So the PCE plume is now imploding on itself. The source treatment is actively working. We can see the evidence of that by the ethylene concentrations that have developed at the site over time. So when we started the remediation, there was barely no ethylene that was generated in groundwater. As we finished the injections and we continued the monitoring, we could see ethylene starting to develop. And now we have also experienced through the collection also of microbial data that the ethylene that we are seeing being generated off-site and away from the areas where we did the Cat 100 injection is thanks to the presence of functional genes that are able to degrade fully the PCE down to ethylene. This is more data that came from the site. So the consultant in charge has been gathering information from this DNAPL location that we found during the remedial design characterization. We installed a well which had about 40 centimeters of DNAPL present in it. After the injection, they kept monitoring the well by measuring the thickness of the DNAPL and removing it every single time they went there. And as we can see, that amount of DNAPL reduced and reduced over time. And in the last pretty much 12 months, we have no more evidence of DNAPL being present. We went back on site collecting more soil data to validate the conditions at the site. We did a sort of one-to-one comparison where we went back into about 8 locations that were previously investigated in 2016. We collected approximately 100 samples, and the outcome of that soil validation was that we have been experiencing a mass reduction of approximately 40 to 50% compared to the pre-remediation condition. Most importantly, also, we installed the duplicate wells close to the original location just to ensure that DNAPL didn't sort of affect the results within the monitoring wells itself. And the outcome of that exercise was that the new MW27 is actually showing 75% less dissolved PCE than the pre-remediation level itself, which makes sense with the overall data. And this is just a nice picture again of how the soil looked like during the remedial design characterization. So this is pure PCE that was just popping out of the clays as we were collecting samples. And this is the evidence gathered because of the CAT 100 injections, where we can see acetate being generated, ethylene being generated, and chloride, which are all byproduct of the use of CAT 100. The other case study that we want to look at is another site in Northern Europe where the amount of contamination is less, but it's a different type of site where we can see how these in situ applications can be made efficient for clients that have to actually redevelop their property. So here we have a case where the redeveloper wanted to be actually extremely proactive during the remedial design phase. He allowed us to kind of plow through with the MIP back and forth across the whole property just to make sure that he knew upfront whether or not there would be any contamination as a sort of surprise that they didn't know yet. We found this nice little source with some DNAPL levels around the large oil water separator that was present at the site. We managed to delineate properly the whole bedrock and how it kind of allowed the groundwater to migrate off-site, carrying, of course, TCE for this site. But ultimately, the important thing out of the RDC for this specific client was that they could much better plan the future use of the land. So they had already a plan of demolishing the existing building. They knew they had to keep one of the buildings standing because the municipality labeled that building as a landmark, as an historical landmark. They planned for an underground parking construction. So the final design was, of course, taking all those things into consideration. So the old basement of this building was pretty much van-sized boulders, so we couldn't work underneath that building. That's why we installed the BOS 100 barrier downstream. We use CAT 100 to tackle again the source at the hotspot, and we didn't inject up and until the level where the client then had established they would start building the parking. That would also help them saving money because there is no need to inject where you're gonna eventually remove soil. And all that led to these results that we can see here. So in the source area, we see the effects of CAT 100 where the residual DNAPL is still present, but it's slowly getting degraded. And over the last 12 months, we can see a clear reduction in all the chlorinated compounds. Whereas at the site boundary, the BOS 100 effect, it's a little bit more immediate. And here we can see how the concentration went down quite sharply from the very beginning. Then there is a sort of equilibrium phase, which we have experienced in the source area. But ultimately, we are keeping concentrations in control. And Mike, I leave the word to you for the case study you have to present.
Thanks, Giorgio. So this is a large chemical plant in eastern part of the United States. Had multiple contaminants, but we're going to focus on the chlorinateds. Next slide.
Yes.
So this is an example of a site where client had a fixed budget, and so this work was done over the course of the last 10 years or so now, starting with that key RDC phase that Giorgio has mentioned. RPI ran all of the soil and groundwater analyses for this site at no cost to the project. And after that, we started with the BOS 100. So the immediate goal was to limit migration of the contaminants off the property. So the BOS 100 PRB was done, as well as some Shallow soil mixing, that was done with activated sodium persulfate. That was in the vadose zone. And then since then, the CAT 100 technology was developed, and you can see that starting with phase 2 through phase 6, the CAT 100 has been used to go back and some injections were done in that PRB where some high concentrations existed, but the bulk of that work was done back in the source area, which you'll see on the next slide.
Sorry, Mike, it was slow in reacting. There you go.
Okay, thank you. So you can see here the different colors represent the different phases of work over the last 10 years or so. The green that you see down there near toward the bottom, that was the BOS 100 PRB area. You can see the red, the blue, and the pink. Those were some additional injections that were performed over the years. And then on the upgradient side, those were all CAT injection areas, as well as the red area to the right of the PRB. And so what we'll focus on is looking at two wells, PDC 14, which is in the red area in the source, and PDC 3, which is down in the PRB. Go to the next slide. So I like this slide a lot because what it shows is, so the blue is that down gradient well. So this is within the PRB itself. And it shows that similar to what Giorgio had shown on the previous case study, an immediate decrease as high as 30,000 micrograms per liter total CVOCs. And those concentrations were decreased immediately post injection, and those concentrations with a few small blips along the way, but the concentrations have generally stayed low, and that was with one application. What the orange represents is what the upgradient concentrations looked like that were up in the source, and these are the concentrations that were ultimately flowing into the PRB. And you'll see that that's represented on the secondary scale on the right-hand side. So you see the concentrations are much higher. And the second vertical line, that solid vertical line, represents when the CAT 100 was installed. And you see that nice slow decrease over time to where we are now. And on the next slide, I broke out that CAT 100 piece into the different degradation products. So we're starting with a mix of PCE and TCE and daughter products, DCE and vinyl chloride. So you can see the baseline concentrations there on the table. And you can see after 1 year and 2 years post monitoring, the concentration decreases. So this is, CAT 100 is a long-term technology, and you can see here we've had applications in the ground as long as 6, 7, 8 years. And so these will continue to decrease. This is just the data that we have to date. But you can see significant decreases immediately for the parent products, PCE and TCE. And this site was unique because we had a considerable amount of DCE to start with, as well as vinyl chloride, but you can see considerable degradations of those compounds as well thus far.
Perfect. Well, thank you, Mike. I guess we have now time for some questions. We have the panel open, as I wrote on the webinar chat. There is a top or bottom bar, depending on your screen settings, where you can open the Q&A box. Feel free to submit your questions.
And I guess, Giorgio, just one comment. Due to the format of this webinar, having it being as short as it is, the project summaries, at least I think the first one that you presented, Giorgio, and the one that I presented, each have standalone webinars or project summaries crafted for those. And so we can provide more information, because I know we went through this fairly quickly.
Absolutely. And especially the first one I presented, we will be looking at this case more in detail in the upcoming REMTech conference. so that there will be a much broader attention to all the, let's say, technical details. We have a first questions coming in. For CAT 100, given the electron donor addition, is the extended performance more than the BOS 100 only? Mike, you want to answer that?
Well, the extended performance, so the idea is that you're prolonging the life of the iron by adding the electron donor, right? So if you're relying strictly on the iron by itself, say in a PRB, over time, we calculate out based on the mass flux when that iron is going to persist, or how long that iron is going to last, excuse me. And so, and that's goes into our design, so that could be 10 years or say 15, 20 years is how we've designed a lot of those PRBs. But in source areas, you are going to burn through that iron very, very quickly. And so by the addition of the electron donor and the bacteria and all that happening within the pore structure of the activated carbon, because we're adding the bacteria to the activated carbon itself. And so the bacteria are adsorbed onto within the pore structure of the activated carbon. They're preserving the life of that iron. And obviously there's a lot of synergies between the abiotic and the biotic pathways.
We have two more questions that just came up. Okay, even more now popping up. Let's see, we have one about concentration. We can stick to that one a second. So does it also work with concentration like 200-300 microgram liter of TCE, also combined with a PRB, for example, at the border of a site? And actually, I can answer that, Mike. I guess the use of BOS 100 doesn't really, or CAT 100, there is no limitation to the concentrations we are targeting, so we can work with very high concentrations, as we have seen in the first case I presented. But the second case that I, for example, presented, the site boundary concentrations were more in that few hundred microgram liter of TCE range, and that's where we saw that beautiful effect of BOS 100 in keeping the plume in control. So the design application and the way that we implement the two technologies can be really tailored for each individual case, and we don't really worry about the concentrations by default. It's just how the design tells us to better use either just BOS alone or BOS together with CAT. We can play with that. We have two questions which came. So we have one question going: how will the success of the project be evaluated in terms of environmental impact and cost effectiveness? And same person was asking, how does this bioremediation approach compare to traditional remediation methods in terms of its environmental impact? So similar question. Mike, you want to answer that?
Sure. So I think from a environmental impact standpoint, I think these applications, as far as I know, our CAT applications, again, the technology's been deployed for maybe 7 or 8 years now, and on all of those sites we have not had to go back and do additional applications. And so I think when you compare it to straight electron donor addition, where those technologies will burn out in the course of, say, a few years, where you have to come back and do additional applications. So that's additional field work. So from a carbon footprint standpoint, after the injection, you're just in a monitoring phase and not having to go back and mobilize and bring equipment back on the site to do additional work. Same thing goes for something like, say, chemical oxidation, which is even more so, where you're going to have to do many injection events, say, in the source areas that we showed in some of these in these case studies, to where you're going to have to come back on a much more regular basis on multiple times per year, say. So from an environmental impact standpoint, I think it's these are very green technologies in that it's not to say that, every technology is a one and done, but to this point in these source areas we're getting, and that's really the key to monitoring that ethylene or like acetylene on the back end to see these daughter products continually generated. And we've got other case studies that weren't presented today where we're doing long-term tracking of the microbiological activity, and we're seeing continued elevated increases of proper concentrations of, say, things like the helicocoides are being sustained 6-7 years post injection with only one application. Does that answer that question, Giorgio, you think sufficiently?
I think for the time we have, I think it does cover it nicely. Yes, sir. We have again 2 questions from the same person. We'll cover it fast, and then we can follow up by email with anybody who has also additional questions. So we have a question going: the soil injections are pretty aggressive. Is the mechanism more soil mixing than emplacement in sands? For PRB, when you inject in, is the emplacement reducing the permeability of the natural soils, so need to design for an increase in plume width? Well, the reason why, as we were discussing, the implementation is a key factor in our injections, is that we can control all these design parameters. So when it comes to injections in sand, we adjust the settings of our systems to ensure that we can increase the flow to rates where we feel turbulent mixing is taking place more than soil separation that we would actually achieve by using different settings when working with clay and silty material. So we wouldn't call it soil mixing per se, but it would be more of a turbulent mixing of the granulated material and solid amendments within the formation when dealing with sands. When it comes to PRB, there is no risk in reducing the permeability because the amount of product we inject, again, doesn't go and affect the permeability of the soil itself. If we work with clay materials, as mentioned, we would create more soil separation type of effect in the soil, whereas as discussed in the sand, we are looking more at a turbulent mixing, so the material will just blend in with the sands and the gravels, and it will not impact the geological conditions. So we do not have any risk in having to increase the plume width at all. I guess, Mike, we want to thank everybody for having participated. I think there was a final question that came in. Do we have 1 extra minute from all the participants? I'll take it as a quick yes, but there is a last question. How old was the contamination? How long would COVC last without treatment? Does the age of contamination influence the remediation? Mike, a quick word on that? Sure.
I mean, I would say at most of these at these sites, we're looking at decades of that these aren't new releases, right? And you do get some natural degradation. The site that I presented had no remediation done, and you could see there was considerable DCE generation, for example. So if you have existing organic carbon and the proper conditions, the proper bacteria, you can get some degradation. But in general, these sites have been monitored for decades and reach a static state of where maybe you get some degradation, but the half-life is so low, or the half-life is so high, excuse me, that your degradation rates are so low that it would take, that it likely will not degrade on its own. And I mean, maybe at the extent, extent of the plume where your degradation rates are equal or greater than your, migration rates, maybe at the leading edge. But when we're talking about source areas like we have today, I would say that the CVOCs were not going to degrade by themselves naturally. Well, we took already almost 5 extra minutes out of people's time, so we want to thank everybody for joining. If there's any extra questions, you're more than welcome to contact anybody at IASCO or AST.
And we welcome you for the next webinar on 14th of September regarding BOS 200 and BOS 200 plus.
I guess just one more comment, Giorgio. I guess first off, thank you everyone for attending, and secondly, this webinar is being recorded, and so we will get that recorded, and we'll get that recording over to Giorgio. So if you are interested in re-listening to it or sharing it with colleagues, we will have that available for you shortly.
Thank you again, and have a good afternoon and a good morning.